Now we want to prove the converse. What do we need for the converse? First, we need that our rate function RWZ is convex. You show this in the way we did before. You choose 2 points and show and look at the point between this point and show that this point is below the average. So then we need the data processing inequality. You know this data processing inequality from information theory. There we discuss this very well. So we suppose that X, Y, and Z form a Markov chain. Then we know that the mutual information between X and Z is smaller equal to the mutual information between X and Y. And the mutual information between X and Z is smaller equal as the mutual information between Y and Z. The reason is the following intuitively. So you can look at this as a system which first goes from X to Y and then from Y to Z. Of course, if you know the mutual information between X and Y cannot increase if you look at the mutual information between X and Z, because it's a degraded form. Z is a degraded form of Y, so you cannot get extra information of that. The same in the other way around. The mutual information between X and Z is smaller equal than the mutual information between Y and Z, because Y is a degraded form of X, and if you have Y and Z and look at X, then Y as the mutual information between Y and Z can be greater equal than the mutual information between X and Z. You can look at the information theory video perhaps or script if you want to remember how we prove this. The other thing we know we choose several times already for converses is the Fano inequality. You look again at the system, and some random variable X is the input and some random variable X hat is the output, and the error probability that X hat is not equal X is equal PE. Then we know that the following inequality holds, that the binary entropy of PE plus PE, the logarithm to the basis 2 of the cardinality of X minus 1 is greater equal than the entropy of X conditional on X hat. Mostly also this time we use this inequality without the minus 1 in the logarithm. Now we apply the 3 approaches. First, we want to show that our function RWZ, for what we showed, that it's approachable, that this is also really the rate function. So let's look again in the same way. We know n times r is greater equal h of w. It's the same argument that we have before, because we have 2 to the n r indices w. So if you look at the random variable w, it have to be n times r have to be greater equal the entropy of w. Then we can make it smaller if we conditioning it on y. So n times r is greater equal the entropy of w conditional on y. And then we can estimate it by the mutual information between x and w under the condition yn, because we can just add non-zero term, like we do it before in the proof. And then we can write the mutual information in the other way. So instead of h of w under the condition of yn minus something, we write h of xn under the condition yn minus h of xn under the condition wyn. That's just the formula for the mutual information. And this we can write also, if you look at the next line, we can also write as individual sequences. So we can sum it from I equal 1 to n, and then h of xi, yi, Normally this should also depend on xi minus 1, but all xi are independent from the future and the past, because we all of them, we assume that they are IID distributed. So minus the entropy of h of xi, and now we write this in this way. And also we have to add this, which we can remove, of course, because for the same reason we can remove it here. So in this we write as yi times w y to the I minus 1 times yi plus 1n, where yi plus n to the n is just the sequence of yi plus 1, yi plus 2 until yn. Then it's the same like here. So we have the same condition here. And this we have to look to add because we look at the individual sequences, but we can remove it. Then of course this only can increase, but we can remove it because this is independent from the future and the past. So here we can also write an equal here. So then we get this formula here. And here now you see why we wrote this in this way. If you remember, in our formula for RWZ, we maximize over all possible u's. So if we choose here some u and show that the bound holds, then we are fine. And that's the reason why we wrote it in this way. Now we choose u, I, in this way, w, yi minus 1 times yi plus 1 to the n. So this is a, remember, this is a sequence from y1 to yi minus 1, and this is a sequence from I plus 1 until yn. Now we just define ui in this way. That means we can write this in this way here. And now we get this sum here. This is just the mutual information between xi and ui under the condition yi. But now, if you remember that we can also write, let's go back. So we can write this difference, the mutual information between x and u and y and u is equal to the mutual information between x and u under the condition y. So that means we can continue in the following way. Now for that we can insert our rate function here, because we know it's equal to this rate function. So we can insert this function here, and make it only smaller. And now we take the sum from I equal 1 to n. What we do now, we add here an n in the beginning, and 1 to the n we put into this rate here. Because it's convex, we can do this. So we can write here n times 1 over n, and then we use the convexity of RWZ, and then we can just write it in this way. So we put in the sum and put out the n. So this is greater or equal than this part here. Now, if you look at this part here, so we know this function here is equal to the estimate of xi. So that means we have here n times the function of 1 over n and the sum of the expected value of xi and xi hat. But this is exactly how we define d. So we know that n times r must be greater than n times rwz of d. And then we know our random coding scheme, which we described in this section, is rate optimal.